Welcome to Grandpa's Railroad. Today we're going to be talking about voltage, current, and resistance. Voltage is the pressure from an electrical power source that pushes the electrons. This power source could be a battery or it could be a regulated power supply, for example. The symbol for voltage is V. And voltage is measured in units of volts. Now, this units is very important because when we work with formulas and so forth, we must put the parameters in with the right units. And we'll discuss more on that later. Current is a measure of the movement of the electrons in the circuit over a period of time. The symbol is typically I, a capital I. And the current is measured in amps. Now, the amp is a measure of the amount of electrical charge in motion per unit time, okay? So 1 amp is equal to 6.241 times 10 to the 18th electrical charges per second. Well, an electrical charge is the charge of 1 electron. So this is equivalent to looking at a point, say in the wire, and 6.24 times 10 to the 18th of these electrons moving by that point per second. Now, you may not be familiar with this scientific notation, and I'm going to provide a link later that gives a video from Khan's Academy, and I like Khan's Academy very much. They have a lot of videos that explain things. The simple explanation for this is that this is 6.241 times 10 times 10 times 10 times 10 times 10, where that times 10 goes on 18 times. For example, 100 would be 10 to the 2, or 10 times 10. 1,000 would be 10 to the 3, or 10 times 10 times 10. So this is the power, and it just means the number of times we would just keep it taking times 10. So this is a huge number of electrons passing per second. Resistance measures how strongly a material or an element resists electrical current flow. We've talked about resistance when we talked about atoms in the previous episode. And the symbol for resistance is R, and the units is ohms. And like I said, we'll discuss these units later, but the units are very important. Hi there, I'm Grandpa, and we're in the garage today to do a little interesting demonstration about water and the analogy between water and electricity. I have a little setup here that I'll explain in a second. What I have here is a pressure regulator, and I have a ball valve. And what this is equivalent to in an electrical circuit is the pressure regulator regulates the water pressure, just like a voltage is the amount of pressure on the electrons. The ball valve is like a variable resistor. It restricts the flow of the water, just like resistors would restrict the flow of electrons. The difference is we can actually see this. And what happens is I've turned the output up so we can see how much water is flowing in our little setup just by observing how high and how much is coming out here. And it's a very interesting analogy that you can visualize, and you know how much I like visualizations. I also have a little hose cutoff valve here that we'll talk about later. I wanted to break in here with a explanation for those who may not be that familiar of what a ball valve is and what a pressure regulator is. A ball valve is simply exactly what it is. It's a ball inside a pipe with a hole in it. It has a handle on it so you can turn the ball within the pipe. If we look at it another way, if the handle is going with the pipe, you'll see that the hole is going with the pipe, and the water can flow straight through the ball. If we turn the handle slightly, we start getting more ball and less hole, and that restricts the flow of the water. And then finally, when it's fully closed, that's when the handle would be this way, you get the ball, the end of the ball, and no water could flow. So that's a simple explanation of a ball valve. A pressure regulator is something that basically reduces the pressure at the output from the pressure at the input. And this is a simple diagram of how one works. Let's say we have a high water pressure here. Basically, the regulator consists of this spring with a valve here, this valve, that will cut off flow. And what happens is, as water goes in here and it goes up here, this water puts pressure to push up the valve. Now you can adjust the pressure by setting this screw or turning this handle. And basically what it does is compress the spring. The more you compress the spring, the more pressure it takes to push that valve up, this valve up, and shut off the flow of water. As you reduce the handle or reduce the pressure on the spring, it's much easier for water on this side to push it up and restrict the flow of new water. So basically, a pressure regulator almost always consists of a spring, a valve, and some sort of screw type adjustment that controls the pressure on the spring, which then controls the pressure needed by the outlet water to slow down the input water. So let's start by, I have it set on the lowest pressure that I can get. And let me open this little valve the entire way. And as you see, as I do, you can just see a little bit of water dripping here and kind of making a mess. But now let's start by increasing the pressure. And you can see, as I increase the pressure, more water flows. Right, I'm going to stop right here and turn it off all the way. Now, my pressure gauge only reads when this is off, so that's only about, I don't know, 5 psi. So let's turn it on and go up a little more. Just stop there and see what that says. That says about 10 to 12 psi, but you can see how the pressure is increased. Let's go further up. Turn this a little bit this way. Go further up. And now we're making a very decent sized nest. So let me turn that off, and our pressure is around 30 psi. So at 30 psi, if I go higher than that, we're just going to make more of a mess and I'm going to get in more trouble. So let's do the opposite. Now that we're up here, we're going to open the valve very slowly. As you see, as I open it just a little bit, you can see just a little bit of water flows, even though we're at the highest psi. As we slowly increase it, the water flow increases. Go further up, again, a higher water flow. Further up, higher water flow. All the way to fully open. Okay, So what we've demonstrated is similar to a circuit. As we control the voltage, the higher the voltage, the more pressure there is on the electrons. And with this valve, the more resistance, the slower the flow of the electrons. The more we open it up, the higher the flow of the electrons. Now, one last thing before we go in and do an equivalent thing with an electrical circuit and measure it is, I want to explain why I had to use this pressure regulator valve. As most of you know, as you turn the faucet on, say, your garden hose or even in the kitchen, if you only open it a little bit, only a little water comes out. But that's not, the pressure is being set either by your well or your water company. And that pressure is constant. You're not varying the pressure. That valve that you're turning is acting like a resistor. So what happens, I have this little valve here, and what happens, I've opened up taken basically the regulator out by opening up full thing. And watch what happens when I open up this valve. You'll see a little pop of water go up. That's because the pressure in this tube, as you can see, is up at the full amount. So if I do it, there's our pop. You see how the flow cuts down because I am limiting the water coming in, but the pressure builds up in this hose as soon as I turn it off. And you see the pop again. So just for correctness, I put this valve in just so that we could truly regulate the pressure, not just have another resistor here and sort of be artificial. Just as a sideline, if you're interested in science, there's a few things you can get away with. Like you may notice I've made a little mess. Well, I can get away by telling Grandma, hey, I'm doing this for science. When I was a kid, I used to take apart the vacuum cleaner, say to get the motor or something, because I wanted it for an experiment. I got in trouble, but my mother let me off a little bit if I put it back together because I told her I was doing it for science. Don't tell your mom this, but it's an interesting sidelight. So we're back inside now, and basically what I've done is set up the equivalent of the water demonstration we just had. Basically I have, this is a power supply, DC power supply, it's variable, and this is our voltage source. I then have a variable resistance here, and then I have 2 meters. The Fluke or yellow meter is measuring the voltage. The red meter is measuring the amperage in milliamps. Now, I don't know whether you can see it, but since I didn't have the right potentiometer, I did have to put a little bit of a array network in to cut the power so that I don't overpower the potentiometer. And we'll discuss that in later versions of how you do that. So basically all I want to do is show that as you increase the voltage or the pressure, the current goes up through the resistor, through the potentiometer. And we can go all the way with this power supply up to 16 volts, and we see that as we constantly increase, there we are at about 15, almost 16 volts, the current kept going. The other thing we can do is, as we saw, if we increase the resistance, we will start cutting the current flow. Even though we're not changing the force, we're cutting the current flow on through the circuit because the resistance is increasing. This is equivalent to the valve or that we had on the water demonstration. And you can see the current flow goes down as we increase the resistance. We can also go the other way, obviously, decrease the resistance, up comes the amount of current that goes through it, while the voltage remains the same. Now we can, same way with voltage, as we lower the pressure or the voltage, the amount of current flowing decreases. Now this isn't meant to be it's just meant to be a demonstration. It's not meant to be a real precise experiment at this point. Now, we talked about units before, and units are very important, and we're going to see that volts is the primary unit for voltage, but especially on ammeters and other things, we'll see we might run into millivolts or microvolts. And this is the fractional representation. A millivolt is 1/1000th of a volt. A microvolt is 1/1,000,000th of a volt. This is it in decimal notation, and this is it in scientific notation. And I mentioned at the end, I'd like to leave a link to Concept Academy. If you're unfamiliar with this scientific notation, go and look at that. We also see that the symbol is volts. This would be millivolts and microvolts. Now, it's very important that we convert from, say, if we measured in millivolts, we convert it to volts before we use it in a formula, and we'll see that later. If we look at current, amp is the main one. The two we'll run into are milliamps and microamps. Now, these are the symbols, again, on this side, and these are the representations. Resistance, we'll run into ohms, mega ohms, which is 1,000,000 ohms, or 10 to the 6th ohm, with a capital M. We may run into kilo ohms, which is 1,000 ohms. That's K with the capital Omega symbol. And then milliohms, which is 1/1000th. That's a little m. Now, I've left out a lot of symbols here that may be run into in other things. So, for example, kilovolts. Well, we're not going to be dealing, that would be 1,000 volts. We're not going to be dealing with anything in kilovolt area. Just like power, watts, we're going to deal in watts, milliwatts, microwatts. If we get into kilowatts and stuff like you do in your house, we're doing the wrong thing. And then just for consistency, I included capacitance, which is in farads, and all the symbols that we might run into in that area. So units are very important, as I said. We need, when we plug them into a formula, if the formula wants volts, we need to put in volts, not millivolts. So we would, for example, if we measured in millivolts and it was 1 millivolt, into the formula we would plug 1/1000th of a volt, or 0.001 volt. I mentioned Khan's Academy, and they have several tutorials on various things, and they're very good for young people, very helpful, very well done, and I highly recommend them. In any of the videos that you see that I produce, if you want to know a little more, sometimes they get a little more sophisticated, but if you want to know a little more than my simpler explanations for the beginner, you can go to Khan's Academy and pretty much find a whole series of videos on any particular subject. Again, they may be more sophisticated, more complex, but if you're interested in any particular topic, please go there. Until the next time, thank God for your blessings, and thank the men and women in uniform, the police, fire, military, for your safety. Thank you for watching this video.